All right, let's welcome everybody. Today we're going to talk about Swift serialization. So just to get right into that, what is serialization? It's all about taking your native domain objects in your app. You know, if you're making a photo app, it'd be photos and users and likes and things like that. In my line of work, I use microscopes, so it'd be objectives and numerical apertures and weird things like that. But it's about taking those native objects and pushing them out into some format that can be either put on a disk or put out to the wire or shared with some other process or some other computer. And this process is known as serialization, encoding, or sometimes even freeze-drying. You're freeze-drying your objects to some format. Going the opposite direction, the terminology is not encoding, but decoding. So this is coming out from some file, some format, into your native objects that you work with. And those are native Swift value types, if you're lucky, that you can work with in your app. So decoding, deserialization, rehydrating, those are all words to describe that. Now this information is one of the serialization framework was one of the tentpole features of Swift 4, and it was really came together as a result of these two Swift evolution proposals. You should be able to, after this talk, really breeze through these proposals, and I'd encourage you to do that if you haven't looked at them already. So what they wanted to do with this new thing called codability, or as the Swift team likes to refer to it as codability, and that'll help you remember how to spell it. This is the Codable framework. In fact, last Halloween, Jordan Rose, a member of the core team, dressed up as a Swift Codable. So this Codable thing strives to be a first-class serialization framework. I'm actually surprised that it made it into Swift so quickly, because there's so many ways of solving this problem, so many JSON frameworks out there. I thought it would be very, very contentious, but it turns out it's a really important problem, because all apps, if they're non-trivial, have to do this. And of course, there is a solution, NSCoding, right now, and NSCoding gives you a lot, but it's good for reference types, not so great for the value types. And what this does is it gives us first-class codability for structs and enums and classes as well. It has type safety. It's pretty easy to use, as you'll see, and it's flexible. You can, unlike NSCoding, where you're sort of stuck in the format that they give you, this is really a flexible format that you can use with a lot of different things. And minimize boilerplate, we like that. And it's format independent, which means you can use it with JSON, but you can also use it with other things, other encoders and decoders. In fact, the Katura talk this afternoon is going to be using encoders, custom encoders and decoders to do routing, I'm told. And David Okun back there is going to be giving that talk. So if you're interested in this stuff, I'd encourage you to go to that one. So just a really quick summary of JSON, because the cool thing about JSON is I can put this slide, it's one slide, and it pretty much describes all of JSON. It's that simple of a format. And there's just a few types. There's like strings and numbers. And there's some other values, true and false, null. And then there's compositions of those things, objects and arrays. Objects work like dictionaries. Arrays work like arrays. In fact, this is so useful and so simple that some people just go wild with it and say, hey, I'm just going to pass dictionaries and arrays throughout my whole app and just use those. It's not really a good idea. But we like native domain objects. You can think of Swift serialization as being a static reflection at compile time or reflecting. You may have seen this in other features of the compiler before. For example, when you create a struct, you get an automatic member-wise initializer. That's sort of automatic static reflection of some kind. There's a new equatable and hashability conformance in Swift 4.1, if you've taken in the new compiler. And of course, there's this automatic codable conformance. And this works by introspecting the objects at compile time and generating code. Now, you've probably seen some blog posts or things about this, but here's a simple example here where I have a struct, a location struct, and all I do is conform to the codable protocol, and lo and behold, because longitude and latitude are also, by default, codable, we get this JSON or a serialized representation down there. So under the hood, what's going on? Codable is just the composition of two other protocols. So decodable protocol and an encodable protocol. And decodable simply is this blueprint here. So this protocol that says, hey, from a decoder, I can initialize myself. Of course, that can throw because you might not have the right format, so it's going to be failable. And on the other side, encodable simply means that it has this method that will encode to an encoder type. So now you're probably wondering, what is an encoder and a decoder? So an encoder and decoder is a simple container. It contains one of three kinds of things. So this is the dictionary or the keyed decoding encoding container are typed on key. They're abstracted on key. And it's the most common. It's like a dictionary, and it's the most common thing you'll be using. Probably 95% of your coding will be using that type. The other kind is the unkeyed decoding and decoding containers. And you'll notice that for that to work, the elements have to be codable. Okay, this is the fish up there. And in Swift 4, this had to be enforced at runtime. So every array was just considered codable by default, and then at runtime it would check and make sure that the elements were codable and give you a runtime exception if they weren't. Now with Swift 4.1, the compiler can check that conformance at compile time. It's called conditional conformance, a great feature, exciting feature of Swift 4.1. And that's for arrays. And then the other thing is a simple decoding encoding container. So an encoder and decoder has one of these three types. It can only be one at any given point. So how do you get that rich representation that we got on the JSON page? Well, it turns out that you can make a nested tree of these types, of these containers. And so that's how we get it. So going back to the keyed decoding container, because that's the most popular one, in JSON, we had the string any. We don't like string any's because we like type information. So what we do is the key that we're abstracting on is actually a type which conforms to a protocol called coding key, which is just one layer of abstraction away from a coding key can be a string or an int. But we like to make it a specific type so that you're not passing strings all through you don't have a stringly interface, as they say. So every stored property in your type that you're going to make codable will get one of these coding keys. It'll be generated a coding key, and there's all kinds of ways that we'll see that we can customize this. So the compiler generates three things for you when you conform to codability. First, it gives you a coding key, one for every stored property. Then it creates an init method for you. And then also the compiler creates an encode method for you. But we'll see that you can override these things if you want. The other little piece of information down here says this codable needs to be part of the formal definition of the model, not an extension. And we'll see that at play as well. So with that, let's jump into the demo. I hope you've gotten the course materials downloaded so that you can follow along with me. And as Tammy said, we have a rover theme here going on. And I've divided things up, so I'm going to open up Demo 1. And in Demo 1, you're going to see Starter. And in there's a project called Serialization. These are separated into little missions. Each mission is its own unit test bundle, so if one mission doesn't go well for you, you can just go to the next mission, it'll all be working. Each one is a so-called pebble in the pitcher, and we're going to put in a bunch of pebbles and hopefully be able to drink. All right, so in this first mission, we're going to implement Codable and test it with some encoders and decoders. So my models, I have a rover here, and a rover runs around on Mars that has a name and a set of photos that it takes. And so I'm going to start by making that codable, so I'm just going to type in Codable here. And we'll see, as soon as I make that codable, we're going to get an error that it doesn't conform to the protocol, and that's because photos right now doesn't conform to the protocol. So even though our name is a default type and Foundation gives us codability for strings, our custom type isn't. So we have to go up the chain, as it were, and make that codable too. So we're going to make that codable. And then the error is going to move from that model to this model. So now we have a URL. Foundation makes that codable. So we're missing codability for camera and this thing called souls, which is the number of the amount of time that's passed since we've landed on Mars. Okay, so camera type. Now this is an enumeration, and if I just make this codable, it's actually not going to work because this is just a pure enum, and it needs to be able to represent this enum. So it has to be raw representable either by a string or an integer, and I'm going to make it raw representable by a string. And of course it knows how to encode and decode strings, so that's going to give that one, make that good. And finally, I'm going to make souls codable as well. And with that, we now have a codable rover. Yay. So if I go down to the testing area, notice I have an instance here and a couple of test methods. So the first thing that I want to do is create a test encode and decode for JSON. So in order to do that, I'm going to first make an encoder, and I'm going to make that a JSON encoder. And then I'm going to get me some data from a given object. So this may fail, so I'm going to have to try encoder.encode. And the value here that I take is curiosity. That's the instance. And then I'm going to print out a string. So data doesn't print very interestingly, so we're going to just force it as a string here. Now, notice, actually, I'm getting an error, you'll see, because it wants to throw, this is going to throw an error here. So we could make this a try bang in our test, and that would go okay. But what I like to do, actually, with my tests is actually make the test, declare the test as throwing. And if the test throws, the test will fail. So it's a cleaner way to handle throwing tests. It's just to make your test itself throwing. So here I am creating a string and printing it out. And it is a UTF-8 string. And now that I've encoded it, I'm going to go the other way and run a decoder. So get the decoder. I'm going to say let decoder equals JSON decoder. And then I am going to get a restored object. So I'll say let restored equals try, because it might fail, decoder.decode. And then I need to pass the type of thing that I'm decoding. So to get a type and pass that as a value, you use the type name, rover in this case, followed by self, the self expression, and that returns what's called the meta type of the rover type. So it's returning rover type as a value. And I'm doing that from data. Okay, so now I am going to finally just call the command dump, which actually uses runtime introspection to look at all the properties. I'm going to dump restored. So there we go. And I think I need to spell restored correctly here. And I should be able to just click on this little triangle here in the gutter, and it will run this test. And it'll run that test and it passes. Okay. So remember I said that it's format agnostic? I want to do that by taking this code in this test, and I'm going to copy that same code over here just to give myself a little bit of a head start. And again, it's complaining because I'm throwing out of this function, so we need to declare it throws. And instead of using a JSON encoder and decoder, I'm going to use a property list encoder. Now, the one little change that I need to make is I have to say encoder, and I set the output format. It has various output formats that it needs, or that it can support, including binary and XML. So I'm going to go with XML, and then I am going to do the same thing here. Of course, I need a property list decoder. So I'm taking the property list decoder, and I'm doing the same thing here. And let's just run that one, and it passes too. Now, if I, at the bottom here, or you can do Command-Shift-Y to bring up the console, and you can see, because I've done these prints, so here is the dump. Here is where I print it out. So you can see, in this case, actually, let me run all of the tests. And I can run all the tests by clicking the outer class definition. So when I run both of these tests, we can see both the JSON representation and the XML representation. Okay, so that's mission 1. On to mission 2. Is everybody good? All right. Okay, so I'm going to click on mission 2 here. In this mission, we're going to just change a couple things about some of the let's do some actual testing. So in mission 2, we're going to make that testing a little bit more formal. And you'll notice that each test has this extras directory, and I put some extra stuff in there to help you. Now, Equatable, for example, is implemented automatically in Swift 4.1, but it's not in Swift 4. So I've helped you out by including stuff like that you don't really care, you don't really need to know about. I've implemented it for you. But as we go on, I'm going to put more and more stuff in the extra stuff because it's things you should already know. So here in mission 2, we're going to formalize our testing a little bit more. And we're going to do that by making a round-trip test method. So this round-trip test method is a generic method. So I'm going to uncomment out the test error that gets thrown from these functions. And I'm going to uncomment out round-trip test. And this just tests the self-consistency of an object. It's going to take our object, it could be any type, because I made it generic. All it has to do is be codable and equatable. And if it can satisfies those two requirements, then I can take it through a JSON decoder and encoder and decoder and compare it to make sure it's equal and make sure we're testing. So it's just a quick test, and it throws an error if they're not equal. So it's a good way to test self-consistency. So that's the round-trip test. The other test that I like to have with my serialized code is an archive test. This is where I actually capture some of the output that I've created in a previous version and test to make sure that that's coming back correctly. This is very useful if you're making production code to have a test like this. So it basically, again, it's abstracted across type, which is codable and equatable. It loads in the type and checks to make sure it's equal to an expected type. So when I save that, it will put the little boxes in the right place, and then I can click on this, and of course it's going to fail right now because I actually have to call the test. So let's call round-trip test with curiosity. And of course this can fail, so I'm going to try archive test with some JSON. Now I've cooked up some JSON for you, as you can see there. So it's curiosity JSON, and we expect back curiosity after we've deserialized that JSON. Okay, so if I click and run the tests, they pass. And so we're going to be using this round-trip test and archive test in the future things just to make sure that we are self-consistent and that our backwards compatibility is still good. All right, moving to mission 3. We are in mission 3 now, and I want to do a couple things with the format. So I'm making some new format requirements, and the one thing that I've done is souls now, if you look at the format, it actually, instead of using value, it actually uses the word souls for the key there. So we could fix this by changing the actual stored property name here to souls. But I actually don't want to fix it that way. What I want to do is use a custom coding key to instruct the compiler how to generate the code. So here I'm going to say enum coding keys, and that is going to be a set of strings. I'm going to make it a set of strings, and it's going to conform to the coding key protocol, and it's just going to have one type in there, and that's the case is the name of the stored property, and the name of the stored property is value. And I'm going to say that that maps to this new key, souls. Okay, now for rover, instead of just being name, it's going to be rover underbar name. So we could solve it exactly the same way, just by adding that coding key. What I've done actually is gone and written out the 3 functions that the compiler would have generated for us had we just conformed to the Codable protocol. So here's the custom keys that it would have generated. Here's the decode method, which, if you look at this, it just gets a container, it decodes from that container a string type, and then it decodes an array of photos from that. So this is, again, just what the compiler generates. And encode looks all very, very similar because it's just going the other direction. So the only thing that I need to do, actually in this case, is change name to rover name. So I'm mapping our stored property name to rover name here. So this is the thing, you should actually at some point burn this into your knowledge. This is how a encode and decode method get created. It gets the container out and it actually does its decoding and encoding on that container. So I have some tests here, and we're going to run the tests, and they pass. Yay. So it supports our new format. Now, if you look in the extras directory, you can see where I've hidden away the stuff. Actually, in mission 3 here. So this is where the instances are located. Just it's out of the way for us so that we can focus on that. So that's mission 3. We're going to be using that code in just a moment. I want to go to mission 4. So in mission 4, I am creating a new requirement on our JSON type. Instead of just having photos being its own thing, it's wrapped in a container called mission data. And mission data it might contain or it might not contain photos. So how can we get this to conform? If we run our test right now, we're going to see that it fails. If I run the self-consistency test, because I have a XT fail there, so it's never gonna never gonna pass. Oops, get rid of that breakpoint. Oh, testing. I might have clicked a little too hard for Xcode. Okay, so it's self-consistent. It's very easy to be self-consistent, but this actual archive, it doesn't support yet. Oh, that's because I'm running test. Let's see here. This is mission 4. Okay. Anyway, what I want to do to this mission is I just want to change it so that it supports this, and it turns out I've actually already implemented it for you here. So I've created a struct and made that codable. So this is a nested struct, and this is why it's passing, is because it's a nested struct and it has a photos array optional, and that makes it so it supports whether it's there or not there. It handles those two cases. And so the automatically generated code just works. So I haven't written anything. But notice we've had to modify our model significantly in order to get this to work. So I had to create a mission data nested class. So it's often preferred that you don't want to modify your model, that you just want to change the serialization around, and so that's what we're going to do. So I have in mission 5. So mission 4 is good. It's all implemented. The test is running. In mission 5, I'm going to go and I'm going to look at how I can get this to work without modifying the model. So I'm going to go back to mission 3 and steal that code that I implemented, the Codable extension. So I'm going to cut that code out of mission 3, and I'm going to flip back to mission 5. I'm going to put this code in, and now we see there's a redundancy error. Swift is complaining. That's because I have the Codable declared on both the standard type and the extension. So I'm going to get rid of the one from the extension. Now, in order to get this to go, we're going to first need to create a separate coding key. So the coding keys, I'm going to make an enum. And the enum is going to be mission data coding keys rather. And that's going to be a string conforming to coding key. And it's just going to have a single type, case photos. Now I'm handling the photos inside of this guy, so I want to take this case and I'm going to make mission data, even though mission data doesn't exist as a stored property here. Mission data. And then if I go to my init method, let's first fix this one up. Notice it's not compiling anymore. That's a good thing. Compiler is actually helping us out here. We're going to make a mission data container. And that one's going to come out of the container. Remember, because this is nested. And we're going to use the method called nested container, and it's keyed by dot, I believe I called it keyed by the type mission data container keys dot self. So it's going to bring a dictionary where the key is that thing, and the keys is dot mission data. So it's pulling out a new container with that. Now, instead of getting the photos out of the mission data, I'm going to get it out of the container. I'm going to get it out of the nested mission data container. So mission data container, and I'm going to decode, but this time I'm going to say decode if present. So that's going to handle that optionality part of it, part of it. Now, of course, this is coming to a non-optional type, so in the case where it doesn't exist, I'm going to want to fall back to just creating an empty array. So we've successfully decoded an object without modifying our model at all. So the next thing that we need to do is implement the decode method, and that's going to follow a very similar format. So let mission data container equal try container nested container keyed by, again, it's mission data container keys dot self, and the coding key is mission data, and then I'm getting out of that mission data container. I'm encoding to that. Now, if we wanted similar, I gotta spell try correctly. If we want similar functionality, let's see. Oh, yeah, we can, actually, we don't have to try. We want this to be actually a var because we're writing to it, so it needs to be mutable. So I'm changing that from a let to a var. And it doesn't have to try because it can push anything at once in there. This will actually work now. I believe it will work. Yeah, it will work. If we wanted to, we could customize it further and only encode it, do an encode if present, if we wanted to, based on whether it's empty or not. But I'm going to actually just continue. on. So that is mission 5. Okay, so this is a good breaking point. Are there any questions at this point? I'm going to continue on to the next section. So we're going to talk a little bit about nil, like errors and polymorphism here. So expressing nil values, it's a big feature of Swift, right? The whole optional being a primary type. And there's a great way to express missing values. And JSON actually supports that really well with null. It has an actual type that supports null. plist, it's a little bit older format. It doesn't really know about nulls, so it uses a sentinel type on string. You use this string $null in a property list. And be careful, because if you just happen to put this string in there, if some guy happens to have a name $null, it's going to come back as null. So some formats are better than others, I guess. And another thing is, I want to stop accidents on Mars. You've probably heard the famous accident with the climate observer that crashed because they got their units wrong. So Swift is a great language to prevent these kind of errors with its strong typing system. A solution to this problem is to use what's called a phantom type. So here I am declaring a protocol called length, and I have two units, which are feet and meters, and those conform to the length protocol. That's just so that's a taxonomy of my types. And then I can create a generic type that uses this, what's called a phantom type for the units. So the actual type, feet and meters, is not used anywhere, but it's used as a way to tag or make a distinct type. And that way you can't assign a distance of feet to a distance of meters. You'll get a compiler error. It's a quite useful thing. You can do it with, like, for example, strings being sanitized versus unsanitized strings, so you don't mix those up. So phantom type's a useful thing in itself. I want to point out a problem, though, with using this and Codable is here I have it's just value in there for the actual measurement. And it's going to, if I use the standard default thing, it's going to give me value, value, value. Well, if I decode that with the wrong type and the wrong unit, it's just going to pull it in as value, value, value. And it's not going to know that, hey, it's a different type. This is all about, you have to know which type you're encoding and decoding with the Codable framework. Something to realize. Now, how could we fix this? We can fix this, and we will fix this in the demo, by actually explicitly specifying, for example, a string for the key. So we'll have to make a custom coding key here in order to do this. And this way, if we try to mix up our feet and our meters, we'll at least get an error. Speaking of errors, Codability has a very nice error system, and the errors consist of various things, like if the types mismatch or if a key is not found, for example, you get these specific errors. And with the error, there's a context-associated type that comes back. So this is an enumeration, and an associated type of context, and it has a coding path, and the coding path is just a list that tells you down this tree where that error occurred. So looking at polymorphic collections, so Codability is a very static solution. So if I have this is like the quintessential polymorphic type, right? You have shapes with circles and rectangles and triangles, and you want to make those codable. You have to do something. You have to create another type or a table. I think a nice Swifty way of doing it is to use this associated type. And finally, handling inheritance. So here I have a sample, and this is a class, notice, reference type, and I'm deriving from this class, and it has a mass and a rock type. And if I just make that codable, it's just going to spit out what's in the base class, but it doesn't do anything for the derived class here. And in order to make this work like so, I need to make my object override the codable methods, and I need to get at the super container from my current encoder. So we'll see how to do that. And that's being done in demo 2. And so in the first demo, I want to show you about Null. So here I have made a photo, and I want it, if you saw in the last thing, we did an encode if present. So by default, when you have an optional stored property, it's going to encode it as encode if present. So it's not even going to put the key in there at all if the thing is null. It won't show up in the JSON at all. And sometimes you don't want it to do that. Sometimes you want it to print, you want it to show the null regardless. And so here in my test, my test is actually going to, let's see if I just run this guy. It's not showing up with the usual things, so just going to make them all fail. Right, so here it actually passed our round-trip test, which is pretty easy, but it doesn't contain the URL key, and we want it to contain the URL key. So with that, I added in the code so this is the code that the compiler would generate for you, this encode and this decode. And so all I need to do if I want it to show every time is just, instead of doing encode if present, just make it encode straight. And same thing with decode if present. I could make it like that. And now if I run the test, okay. Okay. Yeah, so it works that, the comment is that if I have decode if present, it actually passes the test. And this is what the compiler generates for you automatically. So in actuality, we don't even need this decoder method. So we could actually get rid of it altogether. And we could, the only reason we have this member-wise initializer was because we had a decode method. So we could get rid of that too. So we could reduce our custom code down quite a bit by just doing that. Okay, so that's that. So on to mission 2. In mission 2, I have this problem where I have my length in meters, and I decode out as length, or decode out as feet, and if I come back in as meters, bad things are going to happen. It'll pass, or I mean, it'll come in, but it'll be the wrong distance and will burn up on the surface of the atmosphere. So we want to fix this. And so the way we're going to fix it is by creating those custom coding keys. So here I have a coding key for value, but I don't really want a coding key for value. So the first thing I'm going to do is create a, I'm going to go and I'm going to create a little static method, static var unit name string. And this is just going to get the name of the phantom type. So it's going to return a string describing units self, and I'm going to lowercase it. So that's just a useful utility. Now I'm going to make a struct, which is a units key. So this is going to be a custom coding key. And the custom coding key has to conform to some properties here. So I'm going to actually let it add the stubs for me. And it's just a simple matter of having a string value and setting the string value and returning the string value. So it's just going to be self string value equals string value, and we aren't going to use an integer coding key, so I'm just going to make these two coding keys fatal error. So they're just going to call fatal error because we don't want anyone to use this thing as an integer key. The next thing we're going to do is update our method here for building the coding. So we don't, sorry, I skipped a step there. Coding keys. We don't need coding keys because we're not going to use this value anymore. So I'm going to get rid of that guy, the coding keys enumeration. And instead, here, instead of using .value, we're going to say for key is equal to units key and string value. And then we'll call our distance unit name method that we created. And this, of course, cannot fail because it's just a simple assignment. So, and then I'll take that code. So it's also complaining because my container is a container of coding keys, and we just made a custom unit key, units key. So I'm going to use the new units key for getting the container, and then I'm going to encode to that. And so the same thing down here, units key. And I will encode to that as well. And I've just handily just going to cut and paste this units key from there to there. And now what I want to do is ensure that this thing fails. So I'm going to use xct assert throws error with the expression try decoder decode an array of distance meters, because that's the wrong type, self, and from data. So with that, we now fail, and that's a good thing. we now pass our test by throwing that error. So any questions at this point? So we've created a custom coding key here, which is kind of cool. It's a little bit rare to do this, but can come in. It's a useful tool to have in your serialization toolbox. All right, so I'm going to continue looking at mission 3. And mission 3, I want to create an AnyType. Okay, so I want to create one that will handle both meters and feet. And so I've created this AnyDistance class that can support either one. It's an enumeration, and it has those as associated types here. And we can see that in our, I've implemented a lot of it for you because it's just a lot of boilerplate, but we're encoding. We just basically encode one of the two types. And when we're decoding, we get the container as usual, get our coding keys, and then we look and make sure that there's only one coding key, because if it was both meters and feet, that wouldn't make much sense. And then here, notice I'm just implementing I'm throwing not implemented error. So it's not going to pass until we actually implement something here. So this is just a matter of going through our cases exhaustively. So I'm going to do a switch here, a switch on the key, and if it's a meters type, then I'm going to set self equals to dot meters, and I'm going to try distance meters from decoder, and if it's feet, I'm going to get my feet, try distance feet from decoder. Oh, I need to actually get the keys. We've already established that so I'm writing in what a key is. A key is I'm just going to the container and getting all keys and getting the first one out. We've already established that there is one, so it's safe to do that. And with that, our test should be able to bring back both types of feet and meters. Yes. Yeah, we have to specify what type, and right now we're specifying explicitly meters, and thank you. We have to update that to any distance. So it's a type any distance. Thank you very much. And now it passes. Okay, in this last mission, we are going to look at inheritance. So I have a sample, and a sample is like a data sample, and it has a date that it was collected. And there's a derived class, which is a rock sample. There could, of course, be air samples or other types of samples, but a rock sample has a rock type. It could be metamorphic, igneous, sedimentary, all of these different types. And I want to implement this so that it uses, so that it serializes correctly. So currently I have most of it done for you. But we need to fix it up just a little bit. So first, let's look at the init method, which is currently just throwing not implemented. So I'm going to get rid of the not implemented stuff and put in container. So container, we have, it's getting the container, and so it's getting the container and doing the stored properties. Now we want to put something in we have to call our super class and put stuff in the super container. But we want that to be namespaced off. So the way that you do that is by try super.init from a decoder, but instead of just passing in the container, we could just pass in the container, but we want it to be in a nested container called super. So in order to do that, there is something called a super decoder. And so we pass the super decoder for key, and we have a key called sample. So this is going to put it in a container in the superclass. So the advantage of that is that I can't put a stored property that could potentially name conflict with something in the base class. By having it in its own little super container, it's guaranteed to not collide. So that's the init method, and then we just need to do the same thing for the the encode method. So we're going to do try super.encode, encode to container.superencoder, for key sample. And I'm going to run the tests, and hooray, they pass. Hooray for green tests. So here, if I look at the actual thing that got printed, the thing I want to call your attention to is that this sample is part of the super decoder and encoder here. It's the way that we pushed in another namespace into our superclass. Okay, so another little tool for the toolbox. Okay, I'm just going to continue on into demo 3. Or not demo 3, first a little bit of theory. So dates, relations, and encoders. So you might have noticed in that last one, we got date, and the date was just this number from a reference time. This turns out to be, I think it's 2001, January 1st. And the reason I guess they did that is because it's the most efficient date parsing that exists. It's just that one number. Other date parsing is a little bit more expensive. And JSON doesn't have, at the root of this problem, JSON doesn't have a date format. It only has strings, numbers, this very limited set of things. On the other hand, property list supports an ISO 8610 date formatting. So property lists actually just can take native dates. Now you can get our JSON encoder and decoder to support this by just telling the decoder encoder, hey, use this date type. There can be problems with this, and the problem can come in where it turns out ISO 8601 is like, it has many different flavors, or there's many ways of representing that particular date type. And you might want to have a custom date format. And so here I'm creating a custom date formatter. And incidentally, notice I'm making this a static variable. The reason you want to always make it a static variable when you're decoding and encoding dates is because these encoders are very expensive to construct. So highly recommend that you create a static one and use that same one over and over again, rather than do it in a loop, because it'll be very, very expensive that way. So you can take this encoder and decoder and just apply an encoding or decoding strategy here. And that'll work. Or the solution that actually I prefer, that is a little bit against the grain of the framework, is to actually, at the encode level, create my own custom string. So here I'm showing you how I created a custom string using the custom formatter. And the advantage of this is if I go to JSON, or if I go to plist, or if I go to YAML, or if I go to some other thing, because it's done at the encoding level, it's format independent. Another thing I wanted to mention was relationships. When you have complicated object graphs and want to persist those, you have to think about how stuff is persisted. So here I have a rover, and a rover has a bunch of rock samples. And the rock samples might want to know what rover they were collected from. So you want to have some reference back from the rock sample back to your rover, right? At this point, like, bells should be going off in your head saying, circular reference, memory leak approaching. And so the way to fix that, of course, is by making those weak references back to the parent, right? That's a standard pattern. You can look at the DevCon from last year to learn more about that. You can follow a similar pattern when doing stuff with Codable. So here's a convention for solving the problem, is have the rover, or the parent class, be sort of in charge of things. And it restores the relationship back to the child when it decodes. And for children, the children keep weak reference back to the parent and don't encode the parent. And you can do a cool thing where if you don't do this, the parent encodes the child encodes the parent encodes the child encodes the parent, and you make a very large file. Coders. Talking about coders just a little bit, we've learned that they have different capabilities, and there's actually a generic user info dictionary that you can put in a custom key in. And you can look at that key in your encode and decode methods to do custom stuff. I'll show you an example of that. I wanted to say one thing about performance. The Swift, and this is Swift 4, and I checked this out in a recent build to make sure it's relatively the same these days. But you can see that it does pretty good. It's kind of hard to read probably on the slide here, but you have the copy. It does okay, but if you really, really need high performance JSON, there's actually some faster solutions out there. Now, the thing you lose with Codable is just the ability to do all of this interchange between different formats. And you can also implement custom encoders and decoders, and lots of people have done this stuff. Now, we can't do that here because it's not hard code to write, but it's a lot of code to write. And typically 1,000 or 2,000 lines of code to implement encoding and decoding for all your little things. So here's an example of a custom project. It's YAML. YAML ain't markup language. It's another type of language, I guess. But to show you a simple example of how this works, here's our code that you probably looks pretty familiar by now. And I just create a YAML encoder and encode that, and lo and behold, we get YAML. So it's pretty neat that you can do this to your objects and have this, very general way of going to different formats. So a couple more demos left, and we're in the home stretch. So let me think. Here's the first mission. Okay, so I want to be a little bit more flexible here with my dates. And what I've done is I have a sample, and that has a date, and it encodes, and I've created this generic function called dateStringDecode. And it decodes with a particular type. Now, we can look at that function. So it's a generic function that I've written down here. Oh, Yeah, sidebar. Yeah, I could feel the heat. So I have a date decode here, and it takes a custom container type. So C is a container type, and it gets that container type out and formats it. So I want to be a little bit more flexible. So I'm going to create one that can handle all of these different types of date formats. And if you notice, they're pretty similar, except one has some, it shows the millisecond count there. So I'm going to go over to this function, and let me space up a little here. So first I want to add another decoder, and I'm just going to copy this date formatter here and paste it, and then I'm just going to add to it. So this is with milliseconds, so I'm going to get one without milliseconds. Now, if you're using iOS 11, this is just a little side note, there is another date format that they've just recently created called ISO 8601. So you could use that instead of this thing that we're doing here. Just a little side note. So here I created a new format, and then with formatters, I'm going to make this a variadic type. So date formatter, I'm going to make that formatters plural, and then formatter ... and now formatters is an array. Now I'm going to take this throws and put it at the very end of the function, because that means I got through and I couldn't find a formatter. So instead, what I'm going to do, instead of just this one if, I'm going to go for formatter in formatters. I'm going to say if let date equal formatter dot date from date string, then return the date. So it's just simply looping through the formatters and discovering two T's. Discovering if I can, tries to parse it. If it can, great, it returns it. Otherwise, if we get to the end, it throws an error. So going back to the test here, now I can say I want to format with, I can add on a dot ISO, and isn't type inference great there? It just let me put those two formatters in, and now I can run the test. And before it was failing because it couldn't find the different date types, and now it passes. Okay, on to mission 2. There's actually a lot we could talk about dates here, but I'm just going to... So in mission 2, we're going to make... we're going to figure out how to make our relationships work correctly. So the first thing we need to do, so I have my sample, it has sample keys. So I actually put in some printout statements that show you like, hey, it's encoding a sample, it's decoding a sample, it's encoding a sample, and likewise for the derived class, rock sample. And so you can sort of see how things are happening at the console. I have some commented out code here. This is if you just like went ahead and just like naively implemented the coding and decoding, you might write this stuff out. But if you did, you'd get an infinite loop of encoding, or yeah, it just keep trying to encode the parent, encode the, encode the child, encode the parent, encode the child. So we don't want to do that, but I just put it in there just for just for fun. So the first thing we want to do is add a date property to our into our sample. Sorry, we have a date property. We want to add a rover property, so it'd be var rover is a rover, but we want to make this optional type, and we're going to make it weak so that we don't have a memory cycle. And then in our init method for the rover, so down here in rovers init, I'm going to take the rock samples for each rock sample. I'm going to set the rover back to myself. So here I'm actually I'm setting up the relationship here. Now, in the rover's equal operator, I want to actually modify this one. This is a case where the default equal operator will get you in trouble. So here I'm going to we're going to check rock samples, we're going to check the launch date, and then I'm going to do one other thing is I'm going to zip up. So I'll use zip left-hand side rock samples, and I'm going to zip that with the right-hand side rock samples. And if that contains, we want to make sure that it contains rover, and I'm just going to use name rather than a deep comparison, because if we did the deep comparison, we'll get an infinite loop, right? Rover name. Okay, so we're getting close. Finally, in our decode method, we want to restore that relationship. So rock samples for each rover equals self. All right, so with that, we should be able to take this nice hierarchy or graph of objects and do that. Of course, if I have a fail, it's going to fail. But I just want to check that the relationship is restored there in the test, and indeed our object graph is restored when we come back in. Okay, one last mission, and then we're done. So we talked about, or I showed very briefly, that you can have custom behavior depending on a key that you put into your encoder or decoder. And so I want to use that fact, and I'm going to do this by showing a demo of, let's say we want to be really lenient about what objects we bring in. So here I have a bunch of rock samples, and if you notice right here, this guy says metamorphical. So it's spelled wrong. So the house of cards is going to come crashing down. But we don't want that. We just want it to throw away stuff. And this is a little trick I learned at a meetup from my friend Guillermo in the audience. And I want to show you how you can enable and disable this trick. So what I'm going to do is I'm going to make an object called a failable decode box. And it's an abstract type. It's abstracting across model, and all model has to do is be decodable. And the failable box itself is decodable. So I'm going to let model be model, but the key here is that model in the box is optional, and if it fails, it just turns it to nil, and that's good, we're good. So since all I am is decodable, I just have to implement the decodable side of the protocol, so the initializer. So decoder, decoder, and of course this could fail, so I'm going to throw. So I'm going to get my container like I've always gotten. So container is equal to try decoder container. Now I'm going to get the single value container because I just want this one value. Does it fail or not? And then the key is that when I get my model, when I decode my model, I'm going to do a try question mark so it doesn't throw. Self. Okay, so now we have this failable box that we can put any objects that we want into it. If it's able to decode that, great. If it's not, it's going to return nil. So it's like we've lifted up, it's a generic solution. Now we want to be able to turn on and off this functionality. And so the way we do that is by creating a custom key that we can key off of. So I'm going to do that. So in the rover class, I'm going to just create a static let, and I'll call it delete bad samples key. And it's going to be a coding user info key, raw value. And you just have to make this some unique string, so I'll call it rover dot delete bad samples. And it's a failable initializer, but we know that it's not going to fail. I better make it samples. Okay, so we have a key. Now we have to actually do something with that key. So in our initializer, when I go and I get the rock samples, I'm going to, okay, so I'm going to get the rock samples. I want to know first which mode we're in. So right here is where I'm getting the rock samples. So I'm going to say if let delete bad samples equals decoder user info, and so that's the user info that's inside the decoders and encoders. And I'm going to use that key that I made, so it's rover delete bad samples key. So if that exists as a bool, so if that returns a bool, and that bool is true, delete bad samples, then I'm going to want to do something special, else I want to do what we were doing before, just putting in the array. So I'm going to take this, what we were doing before, but instead of decoding an array, I'm going to decode an array of a failable decoder box, or decode box of these rock samples. And of course, this is coming back as a failable decoder box rock sample. It doesn't know how to assign that. So we need to run that through something like flat map and just say, okay, only the ones that are not nil, assign those. So $model. And so this will have the effect of just taking the non-nil ones and putting those in. Okay. So now the last thing that we need to do is in our decoder, we have to enable this functionality. So I actually have the code there commented out, and I just enable that, and away we go. And now you can see it correctly throws out the metamorphical. If I were to comment this out again and run it, we see that it fails. Okay, so that's the last mission. On to the conclusion. All right, so there's a lot of details with serializable, but it's a very powerful framework. I hope you've gotten a sense of what you can do with it is. In the first demo, we talked about just the basics of Codable and the three things that the compiler gives us. It generates that coding keys for every stored property. It produces an init method and a encode method to implement the encoding protocol. And you've seen numerous examples of that, and again, I'd encourage you, if it's still foreign to you, to go back and look at that code, make sure you understand what the compiler generates by default, because to be honest, if you know that, like all of the rest of the talk you can derive from those first principles. I talked about errors and polymorphism, and I showed you a trick for how you can use like an AnyType or an enumeration to statically define what can encode and decode. And it's a security thing to have this static type system at work for you. There's a lot of vulnerabilities out in the wild where someone will decode dynamically an object that they weren't expecting, like someone will inject some other object that wasn't expected. And the static nature of this makes it actually a lot more secure, even though it's a little bit more work on the developer end. Finally, we talked about dates somewhat. It's a big topic, but I showed you like a generic method for selecting multiple date formatters. We talked about relationships a little bit and how you have to be careful about parent-child relationships and how to reform or reconstitute those. And finally, talked a little bit about custom coders. Again, there's other talks. I think the Vapor 3s of the world and Katuras of the world are really heavily using this Codable framework, because when you're talking to different processes, it's so important. And that's it. Thank you very much for attending. If there's any questions that you feel free to ask right now, but I'm going to be at the conference and I love to talk about this stuff, so come up and talk to me about your favorite Codable trick.